Most people assume scaling language models just means adding more parameters. The actual breakthrough is mixture of experts. Instead of activating every weight for every token, MOE architectures use a lightweight gating network to dynamically route each input through a small, specialized subset of the model. During the forward pass, the router evaluates the token representation, scores each expert, and activates only the top K. Backpropagation only updates those active experts, which means you can scale total parameters into the hundreds of billions while keeping per-step compute constant. The math is straightforward. If you double total capacity without doubling active parameters, you get better representation learning without the training overhead. But sparsity introduces a load balancing problem. If the router consistently picks the same experts, the network collapses into a bottleneck. Modern training fixes this with an auxiliary loss that penalizes uneven expert utilization, forcing the router to distribute tokens evenly across the architecture. At inference, routing latency is minimized through fused kernel optimizations and tensor parallelism, keeping the overhead under a millisecond per token. The result is a model that scales efficiently, adapts to domain-specific tasks, and pushes reasoning limits without requiring exponentially more data. If you want to see the actual routing math, load balancing derivations, and how to implement sparse MOE layers, I've linked the key papers and reference code in the description.